Good morning, everybody. Thank you very much, John, for that. Very interesting. Yeah, my name is Julian Edwards from ABB. I'm part of their UK Analytical sales team. I'm here today to talk about effective coagulation control. Just a quick resume, very quick, I promise you. I've been working within the water industry for 25 years. Within that time, I've spent 10 years working predominantly with coagulation control systems throughout the UK on surface water treatment works, and have worked on over 60, at least 60 systems being put in throughout the UK. So this is much more of a sort of a hands-on approach from what we've seen, what we've learned, and what technologies we use to affect good coagulation control. So, yes, sorry, some basics here. The reason why we need to have good efficiency in the coagulation process. Proper coagulation is essential for good clarification, filtration, control of pathogens and disinfection byproducts. And if you get your coagulation wrong, these are the causes that go wrong. High residuals, post-treatment problems, and one of the real nasty ones, microorganisms, pathogens such as crypto getting into water supply. And the additional one of you're not doing it correctly, additional costs in waste disposal and creating things like too much sludge and so on and so forth. Get your coagulation right, and these are the positive sides of it. An optimized coagulation process meets multiple treatment objectives. Sorry for using these words such as maximise and minimise, but they're suitable for this. Maximise removal of particles, turbidity, microorganisms and pathogens. Maximise removal of TOC and DPDs, disinfection byproducts. Minimise residual coagulant concentrations. Where people manually coagulate on surface treatment works, especially in today's times where plants haven't got 24 hours mannings, we don't have full-time scientists on site. What will tend to happen when the site's unmanned, I've had this said to me by many process scientists, they will up the coagulant dose, they will put a buffer on the system. You can get away with putting more coagulant in than you require. You can't get away with underdosing, but you can get away with overdosing to a certain amount. I've had process scientists tell me, we sometimes will up the dose by up to 25%, 30%, even up to 40% more, just to give us a buffer when the site's unmanned in case there's any changes in conditions, and it just gives us a bit of time to get to site and hopefully sort the dose out from there. So big savings to be made in dosing coagulants. Filter performance is something I will come on to, but again, huge savings we've seen through where we've been able to optimize and automatically control the coagulation process. If we are able to basically present good, consistent quality water to filters for an extended period of time, you can get a much better runtime out of your filters. Sort of standard industries is head loss, turbidity, or 24 hours, which comes first before they go into a backwash. But most cases where we've put in automatic systems, we've taken filter run times to 48 hours. We did stretch some up to 72, but it got a bit sensitive, possibly pushing it a bit too far. But we have in lots of cases been able to double filter run times, and the savings in that alone are huge. And then obviously minimise sludge production and minimised operating costs. So the operational challenge, natural organic matter in water is a major concern. So it affects colour, taste and odour, reacts with most disinfectants, influences the disinfection demand. Without me reading down every one of these things, but it's a good reason. Yeah, these are what we're up against. The reason why it's good to get your coagulation process sorted out. Quick slide on crypto. If we can get the coagulation process right, clarification process right, this is where we'll trap this nasty little germ getting out into supply. And if this does get out into supply, it literally can cost water companies millions to clean this up. Because getting an outbreak of this, especially in a highly populated area, it's a real problem for a water company. So if you can get the coagulation process sorted out, normally you can stop this baby getting through. Right. we sort of understand the reasons why we need to coagulate and the benefits of it. So from an ABP perspective, an instrumentation perspective, what instruments are there sort of recognised by the industry that can be used to help you optimise your treatment? So we've got physical monitors, turbidity, conductivity, inorganics. You can go down the list: pH, DO, ammonia, nitrate, phosphate, chloride, aluminium ion, manganese. And then organic monitors, UV organic, and colour. The ones highlighted in red are ones that we specifically look at, which I'll come to now. This is the ABB solution. We have a system, it's a Coagulant dose predictor system, where we're looking at raw water coming into a surface treatment works, and we're looking at 3 parameters: colour, turbidity, pH. Colour being the sort of the main parameter for the coagulant dose demand, turbidity second, and pH behind. So we take those 3 parameters, take a measurement of those, feed them into an algorithm, equate a dose as milligrams per litre. When I say coagulant, it could be anything, typically aluminium ion, ferric chloride, ferric sulfate, aluminium sulfate, PaCO, pretty much the whole range. So we feed those 3 parameters into an algorithm, we calculate a dose as milligrams per litre, and then knowing what the incoming flow of the works is, we equate that milligrams per litre to a volumetric dose, mils per minute, and then we need to get that dose actually accurately dosed into the water. So if we get that bit right, we've got good confidence that we're going to get good clarified conditions. We show dose water pH in here. Where raw waters aren't sufficiently buffered, where people have to add an acid or an alkali to ensure that they get the dose water pH settings right, i.e. all coagulants have an optimum sort of pH band of which they work best in. So where the need for acid or alkali addition is, it's very important that that control is good. That as a raw water is changing, if you are chasing it correctly with your coagulant, obviously you then need to be following that with your pH correction, just making sure you're keeping your pH within the right zones for affecting really good control. So going back to our control system, it's based on raw water, those 3 parameters, what we call feed forward, we dose it. I'll talk about a typical clarification stage. We apply that dose, and then we await the time from where the dose has been applied to seeing the effects of that dose on the outlet of the clarification stage. We basically call it a trim time. And then, just argument's sake, say it's hot bottom clarifier, say a couple of hours, we'd look 2 hours later, we'd be looking at the colour and turbidity coming off that clarifier, and we'd be expecting the colour to fall within very tight bands. I'm talking like 2 or 3 degrees haze, and it could be anywhere from like 5 to 8 to 10 to 12. It depends on the process, the coagulant, and the water. But we're targeting very tight bands where we want to keep that colour and also the turbidity in. If the colour falls outside of those bands, we apply a feedback loop to the main dose algorithm where we will just trim the dose to try and pull the colour and turbidity into those bands. And basically, by doing that, if we're able to present the filters with good, consistent quality water for the clarifiers, we know we're going to get the knock-on results of good water treatment back through the plant through your first stage filters, and whether it's going to GACs or straight out into supply. And then showing filtered final water, parameters that use to sort of confirm that you've got it right at the front end. Again, we find colour is a really sensitive measurement for assessing how your plant's performing. Most commonly is turbidity used off your filters, and obviously residual Fe and aluminium, again to confirm that things are working as they should do. Ensuring accurate representative measurement. Back to basics, it could be teaching people to suck eggs, but it's amazing how often these things are overlooked at the planning stages of when new instrumentation goes in. So just some basic points, but from a really hands-on experience, these make a big difference in how things operate. So where practical, instrumentation to be installed is close to the sampling point. On some sites, it's just not possible to get an instrument close to it, and you can have sample lines of in excess of 70 to 100 metres I've worked on. And where things like that happen, we need to have good high-velocity sample lines. One of the classic things I see regularly is with instrumentation, you've got a sample running through it. Sample looks okay, but what can happen if you've got a series of instruments in line, somebody isolates one instrument to do some maintenance, it just changes the velocity through the whole line, and just that subtle change can strip any sedimentation build-up along the line, which just comes whistling down and goes into your instruments that are still left online. And sort of knock-on effects of that are, if it's an automated system for affecting dose, you're going to be driving up your dose artificially due to the line stripping, and even, which, that's not good in itself, but worst case, you'll be, all this material that's being stripped, that's settled in the sample lines will go into the instruments, and some instruments where you use small bore piping, they're going to block and foul, and then they're going to go down, and they're going to require some significant maintenance to get them back up and running. So it's these sort of things, basic as they are, it's so important to get them right at the beginning. And another sort of point, on sample lines, especially the long ones, just try and keep them straight and as smooth as possible. Avoid inverted top hat bends. They're just all sedimentation tracks that they don't show normally until, say, you isolate a sample or a sample pump trips and starts again. If you haven't been flushing them regularly, these lines will strip and send a load of garbage down the line. So we get all the measurements right, we get all the correct information back to whatever you're using, a DCS, PLC, SCADA, to physically take what you've calculated as a coagulant dose to actually get that dose applied to the work. So just some, again, simple points, but very important. Dosing pumps. Make sure they are correctly sized to cover the whole dose requirement. Seen it many a time where we have to bring in a duty assist pump where things just to cope with extreme conditions where the plant weren't expecting. So it's nice to get that sorted at the front. Full control of dosing pumps locally and remotely. What you can do at the pump, i.e. being able to adjust speeds and strokes manually and automatically, you need to be able to do that locally and remotely if remote is an option. Manual and remote automatic control. These are, a lot of places now, plants are want to control the pumps from the control room rather than at the pump. So again, it's just a case of ease of operation, how operators can work with pumps, work with their systems. If it's made easy for them, they're generally looked after better. Install coagulant flow meters. When I first started in coagulation control, going back about 15 years ago, one of our biggest headaches was we could calculate the dose correctly, but getting that dose applied correctly was another subject. We used to do manual drop tests on pumps where you'd set the speed and stroke, and you'd using a litre meter, you'd time the actual dose rate, and you'd basically superimpose those pump characteristics into the computer. So you had a lookup table, i.e. you were calculating you needed 1 litre per minute. The computer would look at this lookup table, so I need to set the stroke at X amount and the speed at this amount to give me that. That was good when you first did it, but over time, dosing pumps will wear and their output characteristics will change. And if these pump graphs aren't kept regularly checked and updated, what you're asking for to be pumped doesn't get put in, and then you start to lose the efficiency of the coagulation process. So what we always not insist on, but recommend very, very strongly is that coagulant flow meters are installed on the delivery side of dosing pumps. So you're physically measuring the actual dose that's being dosed in, and you control against that. So in crude terms, if you've calculated, I'll use the figure, if you calculate a dose of, you're needing to put in 1 litre per minute, that becomes your set point, and you drive the dosing pumps through whatever method, speed and stroke, until the flow meter reads 1 litre per minute, and you just have a little 3-term control that just keeps tuning it into your predicted dose requirement. And that transformed the ongoing success of our systems, keeping them up online and working efficiently for extended periods. Other one there, litre meters, always need those for manual verification. And the last word there, where automated control of pumps is employed, the control software. Yeah, sorry, a bit long-winded. What I think I'm trying to say is the actual pump control, if it's using 3-term technology, PID technology, it needs to be suitably tuned and responsive to the requirement, i.e. as things change, the pump outputs are changed to drive to that set point, and it's controlled nice and tightly, i.e. you don't get big swings up and down and it takes forever to get to the set point. So just thought needs to be put in there. Just a few pictures showing some typical coagulant dosing pump setups, and this is for one of our sites in Southern Water. It's about a 100 megalitre a day site. Dual 2 processes where we can dose. They dose aluminium and the option of dosing PACL depending on what time of the year it is. It's just a setup showing you, typical installation. Quick operational checklist. Again, it is back to basics, but so important that these things are undertaken. So where instruments are employed to monitor and control the coagulant process, the following tasks should be undertaken. Physically check the instruments are working correctly. Carry out calibration and maintenance tasks as deemed necessary for the application, not always as by the manufacturer. Every application is different, every site is different, every water is different, and so the requirements are always slightly different. So, but they just need to be done to ensure the kit is working properly. Going back to flushing sample lines, absolutely prerequisite, that needs to be done regularly. Ensure calculated coagulant dose is being dosed accurately, i.e. even if you are using coagulant flow meters, you still need to be manually checking that what the flow meter is saying is correct, so you know what's going in is right. And the last one, always suspect a straight line when looking at trended results. If someone's got a straight line from an instrument that's taking measurements, you generally got a problem there. Closing in summary, optimization of the coagulation process is central for the drinking water industry, ability to meet goals, particulate, turbidity, and NMM removal. Accurate, reliable, and representative information on the performance of the coagulation clarification stages is paramount. Sorry, I'm reading this off the thing, but just key points, but they need saying. Something that is, I take very passionate about this. More time and thought should be given to the front end of treatment works. I've seen it so many times where loads of effort and money is pumped into the back end of the works, where they go and stick on some extra filters or GACs, but they don't think to look at the front end, which could be 30, 40 years old, running on really old technology. And when I say front end, actually the dosing end of where you're putting in the coagulant. And if you get the front end right, the back end of the process will generally look after itself. It's if you can keep consistent, good quality water coming from the front end to the back end, half the battle is won. And my last sort of closing point, last salesy bit here, ABB has a complete range of online monitoring solutions to provide the operator with advanced analysis required to increase the efficiency of their coagulation process. And just a little closing slide, just showing Municipal treatment works, clean and waste, and the areas that, as ABB Instrumentation Measurement Products Group, where we can supply product into those areas. And that, ladies and gentlemen, completes the presentation. Thank you all for listening.
Okay, thanks, guys. I suppose we can take questions and answers now.
Hello? Yeah, Derek Thompson from La Hoist. On your first one, your phosphate removal, would you adjust the pH with a liquid line to remove the phosphate as a solid calcium phosphate?
We normally don't actually need to do much pH adjustments on the phosphorus removal, because with our normal electrocoagulation, we do find the alkalinity level rises above anyway naturally, and we just incorporate that into the system. So no, we don't normally add any liquor such as base into the systems for phosphorus removal.
Hi, Eduardo. Julian, the algorithms you have, are they suitable for any type of effort? Essentially, you could monitor your dosing rates. You can automate whatever type of effluent you your dosing. So your algorithms are not just set for municipal wastewater.
No, sorry, our algorithm is set predominantly for clean water. So we're looking at raw water sources, anything from river, reservoirs, from that sort. But it's predominantly for the potable industry.
Okay.
Hello, Ian Wilson. Just a question about the automatic coagulation control. If you have a particular monitor failure, say colour, how sustainable is the dose, is the algorithm until that's repaired?
Okay, the system that we would use, if the colour monitor fails, the system will work on the last known result. It will activate an alarm within it saying there's been a failure, but the last known colour result would be worked to. It would still automatically update for changes in turbidity and pH, which are the other two parameters. So that would be you'd get an alarm. The dose wouldn't suddenly drop off or shoot up, but it would just hold where it was, but you get an alarm to work around.
Okay. Question for David on
Yes.
phosphorus removal. Do you need a separate stage of settlement for the electrocoagulation sludge to settle, or can you do it in line on an existing works?
No, we need a separate separation unit, and for that particular process, we incorporate the system so it fed onto their own settlement, their own settlement tanks. But normally, the only difference is the way you impart the flock into solution. So afterwards, the flock behaves exactly the same as chemical flock. You need to settle it, and you need lamella tanks, DAF units, or anything else of that sort to settle the coagulant out nicely.
Thank you.
My name is Adewale from Osamad. I just want a bit of clarification whether you put into consideration the effect of temperature in efficiency of electrocoagulation process.
For electrocoagulation, on the majority of applications that we've worked on, temperature doesn't seem to have much of an effect on it. It's only when you start using more specialist, they're called DSAs, dimensionally stable alloy plates, for certain electro-oxidation systems, that we notice that operating temperature of above 30 degrees is a bit detrimental. But in terms of water treatment, industrial water treatment, the system never, it's at ambient temperature, so we don't bother with it.
What about when you try to minimize or reduce sludge production?
Again, temperature doesn't really play a part for our system. pH plays a part, and also the coagulant dose. But primarily, we've managed to reduce sludge production through the downstream processes that we managed to optimize before it gets to the settlement tanks.